Welcome back to the machine learning development life cycle. We shall be talking more about data this time around. Now, the very first step to working with data is getting this data. So, suppose we want to build a voice transcription system which entails taking in an audio signal and converting it into the textual information in this audio signal. So suppose we say I am a neural learner and we have this audio signal, we should be able to output this. The very first thing you have to ask yourself is, where exactly is this system going to be used? So if there's going to be much noise in the background, it's important to collect data which represents this kind of environment we are going to be working in. Also, suppose you're building an object detection module and your inputs are, say, 1,000 by 1,000 pixel images, and then this is going to be applied in a system where the inputs are going to be, say, 100 by 100 pixel images. You wouldn't get the same kind of results if you had originally trained this data on a system which takes as input 100 by 100 images. So it's very important to collect data that is representative of the kind of environment in which is going to be used, because basically these algorithms make use of this data to come out with very good results. So without data or without good data and with the best of algorithms, you will always have very poor results. So this has to be noted right from the beginning. As machine learning grows, you have the fanciest of algorithms today, but take into consideration the kind of data you're working with is of prime importance. Now, once this data is gathered, the next thing is to be one with this data. Suppose you're working with data, or you've gotten data from a specialized team which is responsible for getting data. Sometimes we may just take this data and plug it in our algorithms and expect to have the best of results without even understanding exactly how this data looks like or the different kind of details in this data. So it's very important to take a look at this data and be one with it. Now, say we are building a system which differentiates between a cat and a dog, and we've gathered so much data. So we have this 12,501 items, and here we have 12,501 items, and we want to use this to train an algorithm or to train a system which is going to tell us after or help us predict after if an input image is a dog or a cat. Now let's take a look at this cat data set. Here we have this. We've done this intentionally to have this cat error. So suppose we had this data and you didn't actually go through maybe to see that there is a dog in this cat data set. It means at some point, if you have an input which looks like this, which is actually a dog, you would be outputting a cat, because from the beginning you had set from your data that this is a cat. So this is a very simple example of how understanding your data is going to be very important. Now, take into consideration the fact that our algorithm makes use of this data to later on do predictions. We have to make sure that our data actually takes in as many different kinds of cases or environments as possible. So let's go through this data set and see how to try to solve this problem. So here we have this cat. Next we have this. We find out we have different colors of cats. So suppose we had initially trained our model on only white cats, or white cats with a few black patches like this, then this model may find it difficult seeing that this too was a cat. So it's important to take cats with all sorts of colors. Then we have the next. We have this cat. This. Now we see that this cat is with a human. So if you have a model which takes into consideration only cats, that's images with only cats, like we saw in the two previous images, then maybe when the model is placed with, or when we have as input a human with a cat, the model may find it difficult predicting that there's a cat in this image. So it's important to take this kind of scenarios too into consideration. Then we have this, we have seen this already, this kind of scenario. We have this case where we have this two cats of two different colors. Next, this other scenario. So we find that actually this data set covers a whole lot of different scenarios. Now the next problem we'll be wanting to solve is that of data imbalance. In this case, this data is very well balanced as we have 12,500 items, and 12,500 items for the cats. So it's kind of balanced. So we could delete this. Now, suppose we had initially, or say we had here for the cats, we have just 100 cats, while for the dogs, we have 12,500 dogs. You'll find that the model would tend to classify dogs very well, but find it difficult in classifying the cats. So we have to always try to fight this problem of data imbalance, wherein some of the classes actually have more data as compared to the others. Getting back to our voice transcription example, we could look at feature selection and engineering. So it doesn't suffice to get your data and say input it in whatever fancy model we have, but we have to be able to select those features which actually matter, because sometimes we have data which has so much information, and some of this information may not be actually useful in helping us solve a particular problem. Now, in the case of audio signals, it turns out that coming up with a spectrogram that is actually converting the signal from the time domain to the frequency domain will be of great help in training such models. Now, let's look at what we have. We have converted this into a corresponding spectrogram, and this has generated this image. So we've left from this audio signal to this image, which represents a spectrogram of this audio signal. Now we have, say, a 75 by 25 image. That's if we're considering the width by height convention. So we have this image, and this image could be broken down into the red component, the green component, and the blue component. That's RGB components. This will lead to an input which looks like this, where we have this xi, could be say x0. So suppose this is the 0th, or say the first item in our data set. We have x1 equals this 1875 by 3 matrix, which is this input. This 1875 is gotten from multiplying 75 by 25. So we have 75 times 25, 1875 times the three different components, and this is our input. So this is how this input features have been selected. Now let us do some data processing. We have these inputs which then are generally normalized. The reason why I will normalize this is because the gradient descent algorithm functions best whenever we're working with data which is centralized about a zero mean and has a variance of, in this case, say for example 1. That is, whenever our data is normalized, we guarantee that our gradient descent algorithm is going to be the most performant as compared to this kind of data which contains information from say 0 to 255. So when dealing with image data and many different kinds of data, we tend to always normalize before sending it into our model. Now, normalizing is in two steps. We could have each of this data divided by, say, the maximum of all this data, that is from 0 to 255. We have a maximum of 255. So we have xi divided by 255, which actually ensures that our standard deviation is 1. And now doing xi minus mu here represents the mean value for each of the channels. So if for the red channel, we could get the mean value. We have x minus that mean value divided by 255, which is the maximum value we could obtain for that channel. So doing this, we should have this normalized output, which is going to be used now as the input to our model. Let's take a look on how we shall treat these textual information, which is our output. That's because we're going to be having this as input and our text is output. But then our model doesn't understand this text as we do, so we have to put it in a way our models understand this. And generally, the way this is done is by using one-hot vectors. One-hot vectors basically are kind of vectors where we have zeros everywhere, and then we select a 1 on one of the positions. Now, the reason why we're doing this is actually to encode this data. So we could have a dictionary of words. So we have, suppose we have, let's say, 1,000 words in our dictionary, and then for each of these words we just have one position where it's 1. So if we have, say, let's take this example, let's take a simple example. So say we have just 5 words in our dictionary, then in this case we may have, let's say, 1 0 0 0 0. So we could cut this portion off. So we have this, and then this 1 here tells us that whenever we see space, our model should understand that this 1 at the very first point represents a space. And then for, let's say, I, now we have first to increase this 1 at this position represents I. So if we could go, we have space A, B, C, D, E, F, G, H, I. And then we have am is very big, so most probably it's in this 3 dots. Then we have A, so we have space. Then the next word we have A. That neural learner is so big, so it's all in this. Then suppose now that we are working with a new dictionary that's a shorter dictionary, so we could see this clearly or clearer. We have space, so we have this space A, B, M, and neural learner. So we have this dictionary made of this only. So all the words we could use should only come from this dictionary. So we have space, now we have this. We have A 0 1 0 0 0. We have B 0 0 1 0 0. We have AM 0 0 0 1 0. We have neural learner, which takes the last position 0 0 0 0 1. So our model understands that if we have 0 0 0 0 1, we are actually working with neural learner. Another important point to take note of is that when working with deep learning algorithms, we tend to do less feature engineering. So say we're working with some other kind of algorithms, we wouldn't be using only this image to be able to, say, after predict whether the sentence I am a neural learner was made. We would maybe go into this image and try to extract much more features, and this will demand more knowledge about the domain. But with deep learning algorithms, we kind of let them actually do much more of this kind of work. So that's where we actually gain from deep learning algorithms, because without knowing so much about the domain, you should be able to get started already. But it's important to know that the more you get to know about the domain, or the more you get to understand the data actually very well, it's going to make you come out with the best kind of models or the best kind of solution. Taking advantage of the deep learning algorithms or the machine learning algorithms we have today is good, but doing this excessively is not the best of ideas. That is, suppose we have a problem, and doing much of or doing more of the feature engineering would permit you to use a less fancy or a less deep or less complicated algorithm, then that's gonna be a better option, because it actually makes no sense to just leave out this feature algorithms or features engineering section and just count solely on the deep learning algorithm, whereas working or doing more of the feature engineering would have permitted us use very smaller models. And also in cases where we have or we're working with very small data sets, working with deep learning models is going to be very useless, because we're going to have less interesting results as we would have done if we were working with the simplest machine learning models or simplest machine learning algorithms. And generally, when working with these simple machine learning algorithms, we tend to do much of the feature engineering. So this feature engineering part doesn't have to be neglected.